Well, without further ado, hello everybody. My name is Liam Spence. I'm the Mission Operations Manager for the MiTEE-1 CubeSat. Joining me today are Sam Sharma, Alex Below, David Lee, Chris Park, and Wayne Zhu, and we'll be presenting some of the lessons we've learned from the development and flight of the first miniature tethered electrodynamics experiment, or MiTEE-1. In this presentation, we'll give a brief project overview and a background for you to kind of understand where we're coming from, a summary and the mission overview of the MiTEE-1 CubeSat and the lessons we've learned so far. And finally, we'll end with a brief overview of the development of the next iteration of MiTEE CubeSats, the MiTEE-2 CubeSat. Now I'll pass it off to Sam, our plasma science lead, to provide an overview of the MiTEE project as a whole.
Thank you, Liam. So as you can see on the screen, we have the development of MiTEE-1 to MiTEE-2 and then eventually our project end goal. So MiTEE-1 is the first CubeSat iteration for the MiTEE team. It is a 3U CubeSat with a 1 meter deployable boom that connects a small picosat end body to the main body of the satellite. And it is currently orbiting Earth and is midway through its planned mission lifetime. And so MiTEE-2 is the second CubeSat that the team has begun development on, and this design draws heavily on MiTEE-1 with key improvements made from the lessons learned from the MiTEE-1 mission. And MiTEE-2 aims to implement an electrodynamic tether, which is an EDT, propulsion system on a small spacecraft. The end goal of the MiTEE team is to develop the technology needed to operate a constellation of tiny tethered satellites that would be capable of performing controlled orbital maneuvers without the mass and volume penalties associated with traditional propulsion systems. So here we'll provide a brief overview of EDTs, or electrodynamic tethers. So EDTs are long conductive tethers that act as a circuit when interacting with the ambient plasma environment of space, and this system is governed by the Lorentz force. So when a current flows through the tether, the magnetic field it generates interacts with the magnetic field of the Earth to either add or remove energy from the satellite's orbit, and this controls the propulsion of the spacecraft using the tether. So EDTs have a variety of use cases, which include indefinitely extending the lifetime of orbiting satellites, providing quick deorbiting solutions for space junk, or even acting as a deployable communications antenna. The MiTEE team aims to explore a variety of use cases for EDTs to advance the technical capabilities of this technology in small spacecraft. So this is our overall MiTEE-1 science circuit that showcases an example of how our EDT might work. So for MiTEE-1, we use a 6 by 6 by 2 centimeter positively biased metal planar picostat to attract electrons from the surrounding plasma environment based on previous research done and current collections models made. And this then generates a current, which is our tether current for MiTEE-2, that travels up to our HVPS and CCPS electrical power boards, eventually leading up to our thermionic cathode that was provided by E-beam Incorporated, and that emits electrons to balance the spacecraft bias and complete the circuit. The Langmuir Probe is an instrument that we are using to characterize the ambient plasma environment and gather data about electron temperature, plasma density, and plasma potential. Overall, we aim to keep the majority of the system as similar as possible between MiTEE-1 and MiTEE-2. So now I'll pass it back to Liam to provide you with a short overview of the MiTEE-1 payload and mission.
Yeah, so for some kind of initial clarification of system terminology, the main body that we'll refer to is the larger satellite on the top left. This is the total stowed volume of our CubeSat before it is deployed into space. The picosat, or end body, refers to the small deployable device on the bottom right. This is connected to the main body via either a tether for MiTEE-2 and the future missions we'll develop, or by a boom, which is a rigid and shorter object on MiTEE-1. The Langmuir Probe is one of the main science instruments, and you can see that it is connected to the main body for the MiTEE-1 CubeSat. As you can see here, MiTEE-1 is a very complex system. It's a 3U CubeSat with a deployable 1 meter rigid boom that connects the current collecting picosat end body to the main body of the satellite. The main components of the plasma science subsystem that we've used for this mission are the current collecting picosat, an electron emitting cathode, and the Langmuir Probe. And MiTEE-1 also features an omnidirectional antenna array for Earth to satellite communications, as well as active 3-axis attitude control and onboard power generation and storage solutions achieved by uh, batteries and solar panels. So MiTEE-1's goal is to actually take data on the current collection capabilities and ambient plasma environment of low Earth orbit, and this will advise the development of a full EDT system on MiTEE-2 and future MiTEE CubeSats. It launched to space in the early January of this year and is currently orbiting Earth with mostly nominal health data. Unfortunately, however, persisting issues with our communications scheme have prevented us from having full command capabilities of the CubeSat to this point, though we are working on implementing a solution for this issue and have recently been able to extend the license for our mission into December 1st of 2021 for to hopefully achieve full mission success later on. Now I'll give it off to Alex, a member of CDH, to begin talking about the lessons we've learned from MiTEE-1.
Thank you, Liam. So we've categorized our lessons learned into 3 categories: technical, logistical, and operational focuses. Due to time constraints, we'll only be able to present on the main lessons learned from each category, as we've identified many more than just what we have in this presentation. We also recognize that our operational lessons learned are still incomplete, as MiTEE-1's mission is still ongoing. These lessons will ultimately help improve and advise the development of MiTEE-2 and other future MiTEE satellites. Moving on to the technical lessons learned, in reviewing our work for MiTEE-1, we've identified a need to reach the testing phase much earlier in future satellite design cycles. This covers both our subsystem and component testing, as well as operating tests through our radio ground station as early as possible in order to ensure that our communications are very solid early on in the mission. We also identified that we need to greatly simplify the flight computer architecture to ensure that more students, even with basic programming capabilities, such as EECS 280 knowledge, are able to understand and contribute to code development. This is due to our MiTEE-1 architecture being overly complicated due to the use of 4 processors, which all communicated in tandem using a complex and limited simple data exchange protocol, which was inhibited by low memory, small packet size, and slow processor speed. And this increased our complexity a lot, which made it you need a lot more experience working within computer architecture. It made it harder for new members to actually get a foothold into CDH work. Finally, as we transition to non-rigid tethered satellites, from a rigid boom, we will need much more precise and responsive attitude determination and control systems to maintain accuracy anywhere in the satellite's orbit in order to prevent tangling and torsional load on the tether. Now our structures assistance lead, Wayne, will go a bit more in depth with some of the logistical lessons we've learned this far.
Hi, thanks, Alex. Now I will discuss some logistical lessons learned from MiTEE-1. So we have identified that our team needs comprehensive, standardized, and regularly updated team documentation. We have begun developing formal testing documents and schedules for our subsystem and system-wide tests, creating a process for graduating members to properly document their experiences on the team to aid in the knowledge transfer from year to year. Members have also developed onboarding materials to help reduce the learning curve and allow new members to contribute to the team much earlier in the time on MiTEE. Additionally, the team has begun to emphasize the importance of conducting formal design reviews. The benefits of these reviews include the opportunity to identify and clearly communicate the system and mission requirements. We've also noticed that increased effort into organizing and compiling information into formal presentations increases student engagement and provides critical communication experience for those involved. Feedback from both internal and external reviewers also help smooth the development process for MiTEE-2 as well. Finally, one of the larger logistical changes we are making to the team is a reorganization of our team membership breakdown. Here, you can see the MiTEE team structure from this past semester and how it has been throughout most of MiTEE-1's development. The system team, shown in the diagram of the gray section on top, was separate from the sub-team leadership, shown in the gray section on the bottom. Due to the technical nature of the plasma subsystem, the sub-team consulted with postdoc advisors who were not fully associated with the sub-teams or the subsystem group or the system groups, and acted instead more independently. The integration and testing team, the team responsible for building and testing of the final satellite, was ultimately combined with members from the EPS subteam instead of operating as their own independent group. The mission operations team was also not its own team and instead was composed of members with primary roles in the other subteams. Here, you can see our revised team structure that we will be moving forward with beginning this summer. The main changes we've included are adding a chief science officer role to be filled by a student who will lead our plasma team. We will also be making mission ops and INT their own individual subteams that will be led by the mission ops manager and chief engineer, and ensuring that each student has only one primary subteam to focus on, instead of having students split their time between a primary and secondary subteam, as we did with Mission 1 Mission Ops. Since MiTEE-1 satellite is still in orbit, operation lessons are still being learned. But however, we have already identified some lessons learned and we will discuss them here. First, we have concluded that full early mission simulations are crucial for successful launch and spacecraft checkout. This means that the team should have complete mission operations plan months before the launch of the mission. Additionally, analysis and characterization of possible failure modes and potential scenarios should be conducted early on in development before the satellite launches. Having the analysis completed and ready to go will allow the team to quickly and effectively diagnose and address any off-nominal events should they occur. Our team has also discovered that the smallsat enthusiast community can provide very helpful resources to our mission. One component is a SatNogs project, an open source ground station network, which significantly increased the amount of data we were able to receive from MiTEE-1. Earlier integration of this system would have allowed our team to collect even more crucial mission information from MiTEE-1. And so to wrap it up, I'll pass it off to David, one of our OADCS members, to describe the planned development and current progress of MiTEE-2.
Thanks, Wayne. So to provide the context of our discussion, the mission of MiTEE-2 is to study the physical and electrical dynamics of operating an electrodynamic-based spacecraft in low Earth orbit. Our MiTEE-2 CubeSat will implement an electrodynamic tether as a propellantless propulsion system, a deployable communications antenna, as well as other use cases of EDTs. On the next few slides, we'll go over some of the main changes we plan on implementing from MiTEE-1 to MiTEE-2. These will include, but are not limited to, more complex plasma subsystem designs, additional communications architecture for both satellite to Earth and satellite to satellite communications, and more capable ADCS hardware. While we're still early in the development cycle of MiTEE-2, the first iteration of the design will largely resemble MiTEE-1 in science and system design. However, some of the main changes from MiTEE-1 include the transition from a rigid boom to the EDT to add propulsion and communications capabilities. Additionally, MiTEE-1 aimed to have a dual LP system at first to better track the variability in plasma potential. But due to size and storage constraints, we were unable to implement that option. Therefore, a lesson learned is starting to consider constraints sooner to try and fit the twin LP design into MiTEE-2. Moving on, compared to MiTEE-1, MiTEE-2 will have an additional radio attached to the tether that's used as a satellite to Earth communication antenna. In addition, whereas MiTEE-1 only used magnet workers from additive control, MiTEE-2 will have both magnet workers and reaction wheels in order to satisfy the nadir direction pointing requirements. The addition of Z-axis reaction wheels may also mitigate the torsional loads of the tether, that is, the twisting of the tether. I will now pass it off to Chris, a member of the structure subteam, to discuss the EDT physical requirements for MiTEE-2.
All right, so lastly, with the plan change for from a rigid boom to the 10 to 30 meter electrodynamic tether, we've identified some initial physical requirements for the tether. So we've determined that the EDT will need a conductive core surrounded by layers of insulation to protect the core from being exposed to corrosive environmental conditions in low Earth orbit. This insulation will most likely consist of multiple materials that are identified to possess high resistance to atomic oxygen erosion and UV radiation in low Earth orbit conditions. And from the lessons we learned during MiTEE-1's development, we want to implement conducting detailed trade studies and design reviews as often as possible to determine these materials and come to a consensus on the team. The same goes for developing the satellite's deployment system from the initial deployment requirements that we have identified. The first one being that the EDT must be deployed to its greatest possible extent, and its final velocity at the end of its deployment needs to be mitigated to prevent any reactive kickback on the main body and picosat. And we also need to prevent any spinning of the satellite due to the coil winding as the EDT is deployed. So the tether's stored either coiled or in some shape of way in the tether, so that when it needs to be deployed in a straight and constant rate, so that again spinning is not induced onto the main body. And finally, as we look forward as a team, MiTEE-2 aims to be the first CubeSat we develop to study the dynamics and logistics of EDT-enabled spacecraft in low Earth orbit. So by using the lessons that we have learned and we've talked about in this presentation, in our ongoing development of MiTEE-2, we aim to explore many novel uses of EDT technology on small satellites during the mission, and is the next step in achieving our overall project goal of operating uncoordinated constellations of low-cost, highly maneuverable MiTEE small sats in the future. So thank you to the SET Symposium for allowing us to present lessons learned from the MiTEE-1 project, and we'll gladly answer any questions that you may have this time.
Thank you so much, everybody from MiTEE. That was a great overview, and congratulations on the launch too.
Yeah, thank you. It was a very exciting way to start the year.
Yeah, great way to start 2021. I'm sorry to hear about the communications issues. How's that been going, I guess? You briefly mentioned it, but
Yeah, so with the kind of craziness of 2020 and the approaching launch, there were some tests that unfortunately were not conducted fully, resulting in a kind of communications error where the speed from our ground station between transmitting and then receiving is not actually fast enough to keep up with the speed on the satellite from receiving that same transmission and then transmitting back. And so while we have some limited capabilities with that, we are able to, be in a kind of listening only mode and hear the health beacons. I think we showed on one of our slides that we have some pretty nominal health data from the CubeSat itself. We don't have the full capability to uplink commands to it yet. And so that is what we are trying to work towards by speeding up that time to switch between the two transmission modes. And I think actually this coming week, we're going to test out the kind of prototype for this change and hopefully get that capability back for MiTEE-1.
all right, we'll keep our fingers crossed for you.
Thank you. Yeah.
Yeah, but thank you so much for sharing everything. Do you have any questions to start us off?
Sure. So the team is really large. There you got a lot of different sub teams and a lot of, moving parts to design, build, test, also fly and operate a small spacecraft. So what is the learning curve like when you're starting off, and who is allowed to join the team?
So for the first question, as far as like a learning curve, we had a very large learning curve when my kind of year came onto the team, because at that point we had a very mature team all graduate, and so it was left to essentially I think almost it was either almost half or over half of our team were just new members coming onto it. So that was obviously a very big learning curve, and we had to essentially learn how to build satellites as freshmen, sophomore, juniors. But over our time on the team, we've tried to work to really diminish that learning curve, and so make it easier for new members to actually contribute and be feel like they're having a meaningful impact on the team earlier in their time on MiTEE. So within the first part of the first semester, rather than at the end of like their first year. Regarding who can join, since we're a part of the multidisciplinary design program, anyone in the MDP program is able to join us. We've also had people join from outside the program as well, both grad students and freshmen. And so it's very open to anyone who's interested. And we have, I guess, a couple different routes of applying, both through MDP and through reaching out to Professor Gilchrist and, ways like that.
Thanks.
If anybody has a question, feel free to send it in the chat. I actually wanted to ask a question. Do you mind explaining on your logo? You have like Penn State listed there and S3FL, like your affiliations, I guess.
Yeah. So MiTEE-1, I guess, is a very long running project. We actually began development in, I believe, 2013. And so at that point, Penn State was actually working pretty closely with us. They actually supplied some of the solar panels that we used on MiTEE-1 that are in space now. Over the years, that partnership has dropped off a little bit, though we still want to recognize them as a very helpful partner in the project, even if it was many years ago. And S3FL is kind of a similar situation where we, um, especially during like the very early stages of MiTEE-1, we were using S3FL resources quite a bit. And as we have grown as a team and grown into our own kind of lab, we've essentially not graduated, but moved a little bit away. So we're able to keep things a bit more internal to the team. And so that's, we still wanted to recognize that partnership as well, though.
Great, thanks.
Mhm.
We've got a question in the chat. Peter asks, can you discuss the plans for control? Do you plan to stick with rate control or implement attitude control?
Yeah, I think I'll pass this one actually off to, I believe, David is one of our OADCS members who might be able to field that a bit better.
Yeah. So this past semester we've been mostly focused on the Tethered dynamics control for attitude control. That's what I'm saying. And we focused on Tethered dynamics, and so there's different hardwares for that's used for control. One, so for MiTEE-1, we only use magnet torquers, not reaction wheels, and so as a result, we were only able to achieve rate control. We were only controlling the rotation rates of the satellites that are flying out in the space. But for MiTEE-2, we plan to do something more active. We plan to employ more advanced hardware. So we definitely hope to implement like some actual attitude control instead of just controlling the rates. And that's still work in progress. And that we definitely hope to get done for MiTEE-2.
Thanks. Hope that answers your question, Peter. Peter says thanks. All right, any other questions? All right, well, thank you everybody from MiTEE. We're gonna go ahead and transition to our next talk from Blue.